Hello and welcome to this video on Poisson's Ratio and Generalized Hooks Law. So this is still, we're starting the course here with a series of videos on very basic fundamentals on strengths of materials. Introduced the stresses, and now we're thinking about more specific cases and expanding on what we learned before. So we learned about Hooks Law and the coefficient E, Young's modulus, and the relationship between the stress and the strain. Now we'll observe another phenomena that we call here is represented by the Poisson's ratio. It's a property of a material. Of any material will have this property and reflect that on the need to actually generalize the Hooks law. So I'll start with this case here. We have a bar that's under axial loading P. If you do take a point along the bar represented with this 3D block that's following the XYZ given here, you will see that if I take a section at any length here, every point in the section will feel a normal stress P over A. And that's in the X direction, so this is sigma X. For the other sides of the block, there are no normal stresses because I'm not squeezing the bar sideways or top and bottom. It's only extension of the bar axial loading in the X direction. And because there's no lateral loads or transverse loads, there are also no shear, no tau in any face of that block. So it's only sigma X. The question is, if we have only sigma X, does this mean that the bar will only deform in the X direction, or something else will happen? So what happens is, and I'm sure you can do it in while maybe washing dishes, you have the sponge, try to stretch it one way and observe what happens to the other dimensions. You will see that the other dimensions contract when you extend or expand or pull the longitudinal dimension. So that's a very well-known property. It's the volume is fixed. So when you try to pull from one dimension, the other dimensions shrink to account for the constant volume here. So this means that we have non-zero lateral stresses, even if we don't have lateral strains, non-zero lateral strains, even if we don't have or we have no lateral stresses. I don't have sigma z and I don't have sigma y. I have only sigma x. So they are non-zero, all these lateral strains, epsilon y and z, and also beside that they are equal. So whatever strain happens in the z direction is also equal to the z happens, the strain happens in the y direction. Pay attention to what I'm saying. It's not the deformation that's happening. I'm representing it as a strain. So the deformation relative to the dimension, that's the strain we're talking about here. So non-zero equal lateral strains. This is what happens. Now Poisson's ratio come in picture here. So Poisson is a French engineer, scientist who observed that phenomena and kind of now found that the relation between lateral and axial is actually a fixed ratio for any material. So every material will have a Poisson's ratio unique to it, and the Poisson's ratio is equal to that lateral strain over axial strain. Lateral strain can be epsilon y, or it can be epsilon z divided by epsilon x. This negative here is very critical. It represents that inverse relation between the strain in one direction and the transverse direction. So if one direction expands or under tension, the other direction will feel contraction, opposite to kind of the opposite sign. So this negative here kind of fixes that because the Poisson's ratio is positive. It's a ratio. So if epsilon y is positive, then epsilon x is negative. Negative will cancel negative. So the negative here present the opposite relationships between the lateral strains and the axial strain. So if you have a rubber band, when you try to strain it longitudinally tension, we'll find it's kind of contracting laterally. So Poisson's ratio, if it's equal to this negative lateral strain over axial strain, this is what we'll end up with. Knowing that from Hooks law, E, Young's modulus, is equal to sigma divided by epsilon. So now I can say the strain is equal to sigma divided by E. Knowing now that epsilon x is equal to or epsilon y is equal to negative epsilon x times nu. So replacing epsilon x with sigma x over E, I will end up with that. So now epsilon y is equal to epsilon z is equal to negative nu times epsilon x or sigma x over E. Now, going back again to Hooks law. So Hooks law kind of focused on one direction. We're very kind of linear at that time when we introduce it. And even its proof and graphical representation of the stress strain curve is linear. You just hold a bar, tension, and it's pure linear kind of stress block. And we're focused only also on the longitudinal stress and strain. But what about the lateral strain here, even if there are no lateral stresses? So now we need to kind of account for Poisson's ratio and its impact on our presentation of stresses in general in 3D. So Hooks law states that, like we said before, the strain is equal to stress over E. Now this formula is missing the influence of the other segments, so sigma y and sigma z, and their strains, epsilon y and epsilon z, on epsilon x. So we're missing here the axial strain from the normal stress in the y direction, and also the so this one is the lateral strain from the normal stress in the y direction, and the lateral strain from normal stress in the z direction. So now epsilon x is not only dependent on the x stress, is dependent on the stress in the y and stress in the z, but considering the Poisson's ratio and also trying to correct here the direction. So if sigma y is tension causing elongation in the y direction, x will feel contraction. So this is why the negative here is important. So we can generalize now Hooks law by having, instead of one equation relating one epsilon and one sigma, I will have three equations relating three epsilons or strains and three stresses. So generally, in general load cases, we don't have really sigmas happen all over, directions in three directions, but it's good to represent the stress and strain relationship mathematically correctly, to represent that phenomena and relationship between lateral and longitudinal strains. So let's see an exercise here just to implement what we learned so far. So we have here this block, and this block here is made of aluminum, and it's under compression in one direction only of 8 kilo pounds. So it's a force unit kilo pounds. Under this compressive loading, there are this 1.5 inch side here expands, which makes sense. If you're compressing the block this way, the lateral, which is the 1.5 inch, will expand, and also the 2 inch will expand. So we measure it, and we found it's expanding by this amount, 0.132 to the power 10 to the power negative 3 inches, which means the new dimension is just adding this value of expansion to the original length. Now the question asks for finding Poisson's ratio. And part B, calculate the new length of the other lateral dimension, which is 2 inch. So what's given to us? We're given the longitudinal force. We have dimensions. We have kind of cross-sectional areas. From here, I don't have sigma, and I have only sigma in one direction, right? I know the strain in one direction, which is the lateral direction. I know Young's modulus. So let's see here. We want Poissons, right? So Poissons is equal to the epsilon lateral, so the lateral strain over the longitudinal strain. We have to remember the negative. So what's given to us? We given the strain laterally, right? Because the strain is equal to the delta over the original length. I know the delta, I know the original length, and I can calculate now the lateral strain. Remember, it's expansion, so a presenting delta here is positive. And that turns out to be 88 10 to the power negative 6. Remember, strain is the unitless, so I didn't write here inches, so it's just unitless. Micron here is just another representation to 10 to the power negative 6. So now I have epsilon lateral, the lateral strain. Do I have the longitudinal strain? I have a force, can calculate stress of this force, and I think you got it. The longitudinal strain is equal to, using Hooks law, sigma over E. So sigma, I can calculate it by the force over the area, 8 kips divided by the area in inch square, divided by E, which is given to me as KSI, 10,000 KSI. So KSI is kilo pound per square inch. So I have in the upper part here kip inch square, lower part is also kilopounds kip per square inch. So I don't have to adjust any units here. And again, strain is unitless. So I ended up with negative 267 micron. So now I have the lateral strain, longitudinal strain. I can easily now calculate the Poisson's ratio. Remember here, 8 kip is a compressive force. So this is why I have here sigma is negative 8 divided by the area. So the negative here is key. I will use that negative strain for the longitudinal, put it in the formula for Poissons. Poissons already have a negative. So it turns out now that it should be correct now. Poisson should end up with being a positive value. That's kind of a check value for you. Poisson should always end up with being a positive value. All right, so we finished part A. Now part B is trying to figure out the new length and the 2-inch side. All right, what do we know about isotropic material that's under lateral load? There are some transverse strains happening. One thing I know is that the lateral strains happening in both lateral directions are equal. Strain, not deformation. So epsilon lateral will equal to the strain that happens to the 2-inch side, which will equal to the strain that happens to the 1.5-inch side. So I already have the 1.5-inch side strain. The strain is equal to delta over L, so delta is equal to strain times the length that I have. So from before 88 micron, this is the strain lateral, which I was focused more on 1.5 inch. It will now be for the 2-inch side. Multiply that by 2-inch dimension, so that's now the delta. You see it's expansion here, similar to the other side, 1.5 inch. So this means the new dimension, I will add now this value to the original dimension of 2 inches, and I will end up with this little expanded, a little more length than the original 2 inch. So that's kind of covered this problem here. It's kind of a simple implementation of Poissons. We don't have stresses in the other 2 dimensions or directions. I have only one stress and one strain originally in one direction, but it causes strains in the lateral directions also. So that's the end of this part here. It's mainly focused on Poisson's ratio, learning the impact of the relation between longitudinal strain and lateral strains. And knowing that fact now, we adjusted Hooks law, the linear simple form of it, to be the generalized Hooks law, and I can now relate 3 strains and 3 stresses, normal stresses, normal strains on a 3D stress block. Okay, thank you for watching. Hopefully you like the video, and looking forward to have you in future videos. Thank you.